Hello students, this is a brief video that leads through the correct answers and reasoning and a little bit of review of concepts for the 2013 released International AP Chemistry exam, what they have numbered 1 through 25. So what I'll do is go through the correct answers and then talk through any that may need a little bit more enhancement. So for number 1, the correct answer in order to get the element that's showing a +1 charge, if you will, or oxidation state, it would be letter E. To balance out the -2 charge, which we know oxygen primarily shows, there's 2 coppers, so each copper would be +1. And I went ahead and labeled the oxidation numbers that each of the elements in choices A, B, C, and D would be showing. Now, the next group of questions asks about a knowledge of how to get Lewis dot structures. The College Board has go-to formulas that it will ask about again and again regarding bonding and Lewis dot and polarity. So I would definitely know water. So we know water will be oxygen single bonded to 2 hydrogens with 2 lone pairs. So that will be showing a tetrahedral geometry, including all of the electrons, but we would call the molecular geometry bent. And because of the 2 lone pairs, this would be a polar molecule. So this water is a go-to example of a polar molecule showing a bent geometry. Now these are polar bonds because of the electronegativity difference of hydrogen to oxygen, but overall because of the 2 lone pairs and the geometry, it makes it a polar molecule. The other go-to, which is not a choice here, would be carbon dioxide. Carbon dioxide is a go-to example of a non-polar molecule that shows multiple bonding. So these would be polar bonds between oxygen and carbon, but there is an equal distribution of electron density. Each oxygen with its double bond and 2 lone pairs are pulling equally, so therefore a non-polar molecule. So non-polar molecule that shows multiple bonding. Another go-to example is nitrogen. And that, of course, is a triple bond between your 2 nitrogens and 1 lone pair on each. Now, this would be a non-polar bond and a non-polar molecule. The other, amongst the kind of go-to, would be ammonia. Now, ammonia has a lone pair on the nitrogen and then 3 single bonds with hydrogen. Now, the electron geometry, just like with water, would be tetrahedral, but because of that 1 lone pair, then it's trigonal pyramidal. This is a polar molecule, and trigonal pyramidal for the molecular geometry. Now, often the College Board will substitute in phosphorus for nitrogen, which of course will have the same number of electrons for bonding. So pH3 would show this same geometry. The other that is really good for us to know the geometry of is methane. And of course we can substitute out different halogens for the hydrogen, but it's good for us to know that carbon here will form 4 single bonds with the hydrogen, and that will be a tetrahedral geometry. And of course, this will be non-polar because the electron density is distributed equally. Just a reminder too, that the bond angle of tetrahedral is 109.5 degrees. If it would be trigonal pyramidal, or trigonal planar, trigonal planar, it's 120. Of course, a linear geometry, like here in the N2, is 180 degrees. All right, so question 4 through 7, here are our answers, but a knowledge of the Lewis dot and geometries really will benefit us. So if you just know water and you just know ammonia. Now, remember, boron is an oddball. It is stable with a total of 6 electrons. So it comes in with its 3, so this will be our trigonal planar. And then if we know methane, and then of course, if we substitute out silicon for carbon, it has 4 valence, just like our carbon, so it will form also a tetrahedral with those single bonds with hydrogen. All right, so number 4 is asking for 2 lone pairs. Again, if we have just knowledge of these go-to molecules, of course, water is that. Number 5 has the central atom with less than an octet. We just know that boron is an exception, and there's our structure. Number 6, the largest bond angle. All right, we don't have any linear, but we sure do have trigonal planar. This would be 120, where this would be less than 109.5 because of the lone pairs, less than 109.5 because of the lone pair, 109.5, 109.5. So C is the choice. Now this brings up another good thing to remember about the College Board. They are trying to make us nervous. So it seems like we should not be repeating one of these letter choices, but often when questions are grouped like this, we often do. They're trying to make us nervous. So we just have to move forward with confidence and know the answer to 5 and 6 is C. And then for number 7, trigonal pyramidal, that is our ammonia. So if we get to know the ones that, that I pointed out just a bit ago, that really helps. All right, moving onward. So now to some reactions. We remember that Bronsted-Lowry is a hydrogen ion donor if it's an acid. If it's a base, it's a hydrogen ion acceptor. So the reaction that is showing that is B. The acetate is becoming acetic acid and the hydronium is becoming water. So this is donating the hydrogen ion, creating these products. None of the other reactions fulfill that. So B is the choice. If we remember, if it is oxidized, that is a species that is losing electrons, Leo, and reduction is gaining. Plus the hint, it's a single species, so it's the same reactant that's undergoing the oxidation and the reduction. In E, this is the odd time. We should recognize this as hydrogen peroxide. Peroxide is a polyatomic ion that collectively is -2, where each oxygen is showing an oxidation number of -1. Hydrogen is +1. Remember, an element, even if it's diatomic, in its element state is assigned an oxidation number of 0. And here in water, oxygen is showing -2. So here, oxygen, -1, going to 0, that's the oxidation, the loss of electrons is becoming more positive. And then the oxygen going from -1 to -2, that's my reduction. So E is the choice for 8. All right, moving on to these. So gases. So we have this selection of gases. And what we need to make note of is they're all at 1 liter. But they are 2 of them nitrogen and 3 oxygen. They are at some different temperatures and different pressures. All right, so first, do the molecules have the greatest average speed? Unfortunately, the root mean square velocity equation is not provided to us in the equation sheet. So this is one we have to know. Or we just have to be able to recall that what impacts the speed of a gas is its temperature and its molar mass. So the smaller the molar mass, the greater the speed, and the greater the temperature, the greater the speed. So given your substances, now we're comparing nitrogen and oxygen, and nitrogen is 28 gram per mole, oxygen is 32. So I would definitely look at my choices that involve nitrogen versus oxygen. and the highest temperature, which is choice B. 16 rather, smallest number of moles of gas. So if we recall that the go-to gas law, PV equals nRT, I want the smallest number of moles. So if we rearrange, PV divided by RT is my moles. They're all 1 liter, and R is the same, of course, for each one. So we really just need to look at the ratio of pressure over temperature and which one will give us the smallest N. So laying it out, and I even converted them just approximately to Kelvin, each of our temperatures plus 273. So the one that has the smallest numerator and the largest denominator would be B, and that's our choice. All right, 17, the greatest density. If you remember, we can also, from the ideal gas law, get an expression for density. So PV equals nRT. Remember that molar mass is gram per mole. So I can express this as mass per mole. Solve this for N, plug in, and then rearrange things to get an expression of density. So I want the greatest pressure, the greatest molar mass per the smallest temperature. And the combination that yields that is C. So a good reminder, ideal gas law and speed of gas, some good things about gases. All right, now for a clump of questions. All right, 18. First, ionization energy. Remember, ionization energy is the energy required to remove an electron from an atom. The closer the electron is to the nucleus, the greater the energy requirement. Coulomb's law. The smaller the denominator, the greater the force of attraction, so the greater the energy. And they are asking us to compare elements in the same period. And we know atomic size decreases as we go from left to right. So we want to choose the one that is furthermost to the right, which is nitrogen, choice E. Then 18. So they are asking for us to have a grasp of when we put these guys into solution, what they do, and be able to find the concentration of chloride. All right, and I look at my answers really quickly, and they want molarity. Okay, so for every one of these that dissociate, I get 0.2 moles of the magnesium ion, but I will get double of chloride, so 0.4 moles. Every one of these, I get 0.1 moles of chloride. So adding, because I'm putting these both in the same beaker, it's 0.5 moles. And it's telling me I'm in 500 mils, so 0.5 divided by 0.5 is 1. So I'm 1 molar in chloride. And that is exactly the choice that we're given, or the correct answer. Okay, number 20 is just asking us to be able to pick an element that will behave similar to magnesium when it becomes an ion. So barium, being a member of the alkaline earth metals, will form a positive 2 as well. And so B is the choice when you're combining with fluorine. In D, that is just some simple stoich. I did do the stoichiometry to handle each reactant separately, but we could do them that for every 3 moles of carbon dioxide, we get a total of 6 moles, but I did do them separately. I even did the long division to make sure I'm getting the correct answer for that value. Remember, we're not permitted a calculator on the multiple choice section. And so it definitely is choice D, just some simple stoich. Number 22, it's asking us to remember what a nuclide symbol is. And a nuclide symbol shows us to the top left the mass number, which remember is the number of protons and neutrons, and then the atomic number is the bottom left. And if this had a charge, if it was an ion, it would show it as an exponent to the right. There's nothing, so we assume it's neutral. So to be this version of iron, there must be 26 protons. If it's neutral, 26 electrons. Subtracting 56 and 26, we get 30 neutrons. So the choice is A. Okay, electron config. So if we can remind ourselves of electron configuration and how it builds on the periodic table. Remember, we have our S block, our P block, our D block, and our F block, and we will fill the S and the P per the same period number. So 1S, then 2S, 2P, 3S, 3P, 4S, 3D. Remember, D is 1 minus the period number. Then we go back to the P block, same as the period number, 4P, 5S, 4D, 5P, 6S, then we get the F, 4F, it's 2 minus the period number, back to D, 5D, 6P, and so on. All right, so it's asking us for an excited atom. So it would be one that it is not obeying the off-Bohr principle, which is an electron takes the lowest energy position that it can hold. So we would want to fill the 1s completely before the 2s, completely before the 2p, and so on and so on and so on. Choice E, you have put an electron in 3p before completely filling the 3s. All the other configurations honor the off-Bohr chart. So E is definitely our choice. All right. And then 24. So as long as we have, remember I said those go-to molecules. So ammonia, and then, of course not methane, but having a good understanding of methane gets us A, B, and D, and then nitrogen is that, go-to triple bonded nonpolar bond and nonpolar molecule. So just knowing a couple of these can really, really deliver some good points. So if you have different elements, they're probably going to differ in their electronegativity enough to be a polar bond. However, for molecular polarity, we look at the entire molecule and judge if there's an area where the electrons will reside more often due to a very electronegative element or a lone pair. So the choice, of course, is D. These individually are polar bonds, but overall the geometry balances the electron density. So D is definitely our choice there. And then in 25, we are being asked for some stoic, but to know the relationship of Avogadro's number. So we could honestly just look at this and say, oh, that is half of Avogadro's number. So I'm reacting half a mole of hydrogen. You're told this is an excess. So if I react to half a mole, I'm only going to create half of what I normally would expect of HF. So only 1 mole, and 1 mole is 20 grams for HF per mole. Or you could set up the stoic, and hopefully we could see, oh, this will be 0.5 times 2 is 1 times 20 is our 20. So that's a just explanation of what the adjusted exam is calling 1 through 25.